Hello, Algebra 2. Let's go ahead and go over our guided practice for Lesson 9.2a. So the first thing we're going to do is we're going to define angles on a coordinate plane, and then we're going to learn how we can rewrite those angles in something called radians. So let's go, first of all, take a look at what that means to draw an angle with a given measurement in standard position on a coordinate plane, and then we're going to find some other angles that we're going to call coterminal with that angle, and we'll see what that means. So for guided practice 1, we're to write 65 degrees as an angle on a coordinate plane. Here's how it works. So you'll always start here on the x-axis on the positive side. That's your starting point, and you will always open your angles counterclockwise. So you'll go as far as you need to and stop then when you get to the angle measurement. So 65 degrees is less than 90 degrees. I've marked off 90, 180, 270, and 360, a full way around the entire circle, so that you can kind of see why 65 degrees makes sense here. It's a little more than halfway between 0 and 90 degrees. So I'm doing an approximation of how wide I'm opening it up, but notice it is less than 90 degrees, but way more than 0 degrees. The halfway point would be at 45, so I've drawn my angle larger than 45 degrees. So that's a positive measurement, going 65 degrees. Well, let's see. If I went all the way around the circle again and added 360 to 65 degrees, I'd have another angle that I would say is coterminal to this red angle. So over here I am adding 360, 65 and finding out that 425 degrees would also be this same angle. It would be coterminal with the 65 degrees because it would take us around the circle one full more time. We also can think about starting at the x-axis and going in the negative direction. So this green curve here shows us what happens if we go around and meet this 65-degree angle by going negative. So we would have to go, well, let's see, 90 degrees, 180 degrees, 270 degrees, plus a little more. That'd be more than 270 degrees. In fact, it would be a total of 295 degrees to the left, or counter or clockwise to start at our x-axis and move all the way around to our angle that is coterminal with 65 degrees. So here I've taken my 65 degrees and I've said let's go backwards. Let's go around 360 degrees the other direction, and that will land us at negative 295 degrees. So negative 295 degrees would be the same exact angle as the 65-degree angle. It would be this one right here. Guided practice 2 says to write 230 degrees in standard position on our coordinate plane, and then to find positive and a negative number of degrees coterminal with the original angle. So we're going to start here again at the x-axis, and we're going to go counterclockwise. We'll go past 90 degrees, we'll go past 180, because 230 is more than 180. And we'll stop before we get to the 270 degrees. So again, I'm kind of approximating where it would be here. So it's going to be a little bit more than halfway. So let's see, I'm going to draw this red curve and stop here and label it 230 degrees. And then I also can start at my x-axis and go in the negative direction. That would be the clockwise direction. So I'll go more than 90 degrees, and to meet it right here, 90 plus 40 would give us the same exact angle here. So my coterminal angle, so if I start here and I go positive, that's counterclockwise, and then I add another 360 degrees, albeit the same angle measurement, 230 degrees. And 590 degrees would be exactly the same angle. Or I could start here at my x-axis and I could open it up by going clockwise, that's the negative direction, and I would stop 130 degrees going in that direction. So 590 degrees, negative 130 degrees, and 230 degrees are all coterminal. They all describe this angle. Open it all the way up and stop here. All right, our last guided practice problem of this type of problem, write 300 degrees in standard position. To do that, we will start here at our x-axis, and let's see, we'll go all the way around here, and we will stop here at 300 degrees. So notice we're more than 270, starting here and going all the way around. We also can start here, and we can go 60 degrees clockwise, and that's going to land us in the same place. So notice here, the 300 minus 360 gives us negative 60 degrees. So it gives us exactly the same angle, either going 300 counterclockwise or 60 degrees clockwise will land us at this angle measurement here. So we always start at the x-axis and proceed around and our 300-degree angle would be right here. All right, so moving on now, we're going to develop a new idea, and that's the idea of measuring angles in what are called radians instead of degrees. We're actually going to be measuring them both ways, but we need to be able to go back and forth between those two ways. It opens up a whole nother world of opportunity here to understand our relationships that happen in our circles and with our trig functions. So to go from degrees to radians, and you're going to see that word radians reminds you of radius, and the measurement in radians actually is very much tied to a radius of a circle, and we'll see that in our thinking bubble in a minute. But to go from degrees to radians, you're going to multiply your degrees by pi radians over 180 degrees, because these actually measure the same amount. Pi radians is exactly the same amount as 180 degrees, and we'll see why in just a minute. If we have a radian measure for our angle and we want to get back to degrees, we would multiply by the reciprocal of what we saw over here, 180 degrees over pi radians. Okay, so why is pi radians the same thing as 180 degrees? Well, we know all the way around a circle is 360 degrees, and we know that the circumference of a circle is 2 pi r. So the number of radiuses times 2 pi takes you all the way around the circle. So that's why we would be able to state that 360 must be 2 pi times the number of radiuses. 2 pi radians then takes you all the way around a circle. And of course, if you divide 360 by 2, you get 180. Divide 2 pi by 2, and you get pi. So 360 degrees all the way around a circle is 2 pi radians, which is all the way around a circle. 180 degrees halfway around a circle is pi radians, halfway around a circle. So we're going to get used to the idea of this measurement of radians, which matches our measurement in degrees. It's just another way to talk about the number of degrees in an angle, kind of in the same way that we can talk about temperatures in either degrees Fahrenheit or degrees Celsius. They can mean the same thing, but just are measured on a different scale. All right, let's practice going back and forth between radians and degrees now. So guided practice 5. We're asked to change 135 degrees into its radian measure. To do that, we're going to multiply by pi over 180. Now wait, no, when we're switching from degrees to radians or radians to degrees, we know that we've got a ratio here that's got pi and 180. The question is, which way do you need to write it? Here's how I remember it. So I want the 135 degrees to go away, so I need to put the degrees measurement so it'll cancel out. So that means it's going to have to go underneath here. So my degrees will be in the opposite positions. So pi over 180 will be what we multiply by. And then we set about simplifying. I'm dividing here by 5, and I get 27 pi over 36 when I cancel out by dividing by 5. And then I can divide both 27 and 36 by 9, and that gives me 3 in the numerator and 4 in the denominator. So my simplified form of the radians measurement for 135 degrees is 3 pi over 4. It's a little bit less than 180 degrees because pi is the same thing as 180 degrees. Our guided practice 6 also asks us to change an angle measurement into radians. This is a negative angle measurement, which means we would start at the x-axis and we proceed clockwise if we were drawing the angle. We're just going to carry that negative sign right along as we change our negative 50 degrees to radians. This time, we're going to multiply by pi over 180 because, again, we want the degrees to cancel out. So we are using the same ratio when we work out guided practice 5 and 6. Go from degrees to radians, you multiply by pi over 180. And again, we want the degrees to cancel out, so that's why we're putting 180 in the denominator. And then we set about simplifying that, dividing by 10 over 10 gives you negative 5 pi over 18. And that's as far as you can reduce that fraction. So you're done. That's the radians measurement for negative 50 degrees. All right, now we're going to practice going from radians degrees measure to degrees. All right, so we're going to change 5 pi over 4 radians to its degree measurement. So what do? Well, we take our 5 pi over 4, and this time we're going to multiply by 180 over pi. So remember last time we were multiplying by pi over 180, but this time 180 over pi. We want the pi's to cancel out. That's how I remember that it's 180 over pi. We want the pi's to cancel. So the pi's cancel out, and we have 5 times 180 over 4. I'm going to divide my 180 and 4 by 2. That gives me 5 times 90 over 2. And then I'm going to divide by 2 again. 5 times 45 is going to give me 225 degrees for the number of degrees. That's the same thing as 5 pi over 4. All right, one more practice with changing a radian measurement into degrees. We're asked to change pi over 10 into its number of degrees. So again, we're going to multiply by 180 over pi. We want the pi's to cancel out, and that's going to get us 180 over 10, which is 18 degrees. All right, now we're going to use this idea of radians as our measurement for our angles to be able to calculate the length of an arc. And here's a picture of an arc. How long is it from here to here? And the area of the sector, that's that pizza piece or that pie piece here. A sector is like a pizza or a pie piece. What's the area of that yellow sector? All right, so we have some formulas. I'll explain how they and why they work in a minute. Arc length is S equals R theta, where S is the arc length. That's this measurement from here to here. R is the radius. We're familiar with the radius already. And theta is the central angle measurement as long as it's in radians. Now you can see why we were learning how to use radians. This formula only works if this angle measurement is written in radians, not degrees. The area formula is A is equal to 1/2 R squared times theta, where R is the radius, and again, theta is the central angle measure in radians. Okay, why do these formulas work? Well, here's where we can think them through. If we write the ratio of the angles, the angle theta in this diagram here, that angle theta, compared to 2 pi, which is all the way around the circle, then that ratio would have to be equal to the arc length, this length here, compared to the entire circumference of the circle that we know is 2 pi r. So we have this angle ratio equal to this length ratio that we know has to be true. And so we simply solve for S. So I'm going to use cross products here and get S times 2 pi equals 2 pi r times theta. And then my 2 pi's cancel out, and I'm left with S equals r theta. That's where this formula comes from. I can do the same thing to find out why this area formula works. I can compare the angle measurements, my angle theta, to 2 pi again, the full number of radians all the way around a circle, and that would compare then to the sector area compared to the entire area of a circle, which we know is pi r squared. Again, using my cross products, I can solve for sector area. So sector area times 2 pi is pi r squared theta. I can cancel my pi's out, and my sector area would be r squared theta divided by 2, and that means the same thing as 1/2 r squared theta. So there we have why these formulas work, where they come from, and so now we can use them. All right, example 4, we're asked to find the arc length, and in your book it shows this, I think it's a baseball diamond, and there we're asked to figure out the arc length here and the sector area, the yellow area. So the first thing that we need to do is realize that because this is a right angle here, that this is 90 degrees, and we're going to change that into radians because we're going to need our angle measurement in radians in order to use the formulas for arc length and sector area. So changing 90 degrees in radians, I'm going to multiply by pi over 180 degrees. I want the degrees to cancel out. That's why I'm putting the pi on top and 180 on the bottom. And that's going to give me pi over 2. So this angle here, this 90-degree angle, in radians is pi over 2. Now I can figure out my arc length. S equals r theta is the formula for arc length. So S is equal to 180, which is my radius right here, times my theta, which is pi over 2 in radians. 180 divided by 2 is 90, so 90 pi. And then I'm going to use my calculator to multiply 90 times pi and get 282.6 feet if I'm using 3.14 for the value of pi. Now finding the area. Here's my area formula, 1/2 r squared times theta. So I'm going to put 180 in for my r. I'm going to put pi over 2 in for my theta. And then I'm going to use my calculator to help me out. I'm going to multiply 1 times 180 squared times pi. I'm going to take that answer and divide it by 2 times 2 is 4. So divide by 4. And this is the value I'm going to see on my calculator. So 25,434 feet squared. Your book rounds that off to the nearest 100, 25,400 feet squared. Either way would be fine, but I'm going to go ahead and just round off to the nearest whole number because I can. All right, that completes the guided practice for this lesson, so make sure this is all in your notes and refer back to it as you are working through your homework problems. We'll see you next time.